Hello, everyone. My name is Salah Farouqi. I am the R&D scientist at Petrolern. Today, I will be hosting this session. I would like to wait for another few minutes just for people to join us, and then we will start the session. All right, I think we're good to start now. Hello again, everyone. My name is Salah Farouqi. I am the lead R&D scientist at Petrolern. Today, I'll be hosting this session. This is the second talk from the Petrolern at Home seminar series. The main objective of this seminar series is to keep people learning during this depressing time with the hope that you all pass through it safe and sound. Our plan is to have 2 talks per week on a variety of topics related to oil and gas, geothermal energy, and carbon capture, utilization, and storage. We have 6 interesting talks scheduled for April and 8 for the month of May. I would like to thank all the industry experts who accepted to give a talk for us and all the participants for their time and support. We are now currently working on the schedule for June. So if in case you are interested in giving a talk as part of this program, please don't hesitate to contact us at info@petrolern.com. Also, please make sure, please mark your calendar for this Friday, April 17th. We are going to host Dr. John McLennan from University of Utah for a very interesting talk on the most recent update of the Milford Fork geothermal project. All right, before introducing our speaker today, I would like to ask everyone to mute the microphone and turn off cameras. If you have any question, please type your question in the public chat session. We will try to answer as many questions as possible at the end of the session. And one last thing, if for any technical or non-technical reasons you could not stay with us until the end of the session, don't worry, we are recording all the talks and we will share them with you on our website. Okay, now I have the pleasure of introducing our speaker, Dr. Alan Cohen from Petrolern. Dr. Cohen is our business and technology advisor and serves on the Development and Production Committee of the SEG. He has more than 35 years of industry experience in leadership and senior advisory position in upstream E&P operations and technology and in the geosciences and subsurface engineering. He served the United States as senior executive in the Department of Energy, was CTO at 2 technology companies, and chief geophysicist at Shale for North and South America. He was also adjunct professor professor of geology at University of Louisiana. He is very well recognized in areas such as technology integration, rock physics, pore pressure prediction, and machine learning. He holds a PhD from Harvard and a Bachelor of Science from McGill University. He is very passionate about energizing the next generation of scientists and engineers to work on problems that are important to our world. With that, I would like to turn it to Dr. Cohen to start the presentation. Please, Alan.
Thank you very much, Salah. Hey, I want to thank all of you for attending today. It gives us something to do while we are sort of hiding and keeping separate during this COVID-19 crisis. So I wish that you are all in good health and are with your friends or families and are continuing to learn. I want to talk today about technology integration and collaboration. Many people talk about it. It's sort of a difficult thing to do, but there are some successes. And there's a very interesting case history from the United States Department of Energy that I want to share with you today. So you'll learn about what the Department of Energy does, where I spent 2 years of my life. You'll also learn how to interact with the government, and you'll learn some fascinating things that they're doing in the area. Well, I'll talk today about shale oil and shale gas, but they work in a number of different areas. But we'll use the unconventional shale reservoirs and what the government is doing and how they're making progress, and use that as an example to describe technology integration and collaboration. So here are some fundamental principles. The first quote from Stephen Covey that many of you may know. He's passed away, but he was a very famous author and social scientist. And he wrote a very famous book called The 7 Habits of Highly Successful People. And he talks about synergy. Synergy is what happens when 1 + 1 = 10 or 100 or even 1,000. It's what happens when 2 or more entities, 2 or more companies, 2 or more people, 2 or more disciplines decide to really work together and to build something that's just much better than the sum of their individual parts. So I've been working technology integration on and off, as well as doing my regular day job for the last 30-something years. And I have learned that technology integration isn't just building advanced workflows where you integrate all the technologies. That's the technical aspect. And that's actually difficult, but it's probably the easiest part. You also have to get different organizations to work together that would ordinarily not want to work together. And you may want to get some experts in certain technical disciplines who are very high level in oil companies and service companies to work in a different mindset. They like to work a certain way, and now with your help, the world is going to change. And we need these people to come along and to change because they can influence all the other technical people in their companies. I want to give you 3 examples that I've worked on, the last of which is government. I've removed the names of the companies. So the first example, these are all actual examples, real examples, not made up examples. So I've worked at a number of oil companies, and you won't know which one this is, hopefully. So an unnamed oil company had a problem because some of the projects it had invested in were profitable and others lost money. And they went back to look at how they were estimating reserves. And these reserve estimates changed, They have big error bars on them when you start in early exploration. And when you get to your final investment decision before you commit lots of dollars for field development plans, those error bars are tighter and the mean estimates may have changed. But that particular company didn't really look at the error bars. They only looked at the mean values. And as a result, they made some mistakes. They didn't pay enough attention to downside risk. And in that company at that time, the geoscientists and the engineers who really needed to work together were not communicating well. And the exploration and production divisions, and especially their management, were focused only on their own profit and loss statements and were not working together. And the company experts had their own special ways of doing things that they didn't want to change. We were actually able to solve that problem. Next. I was CTO at a number of companies, and this is one of the ones that I worked at. It was a company that had 3 business units, and before the company formed, these were 3 separate companies that were merged together. It was important for the overall company and for the clients that these business units work cooperatively, and that we design a workflow that hooked all their technologies together. But the company, even though it was one company, was still being run as if each unit was separate, with its own profit and loss and its own incentives. The clients, on the other hand, wanted, and the CEO needed integrated services across all business lines, especially for large international projects. We were able to solve that one as well. The one that I want to talk to you today is very interesting, and we made significant progress. We means many, many people working on this. I'm just telling the story. The Department of Energy invests in shale technology, as much as $50 million a year. The yearly budget depends on what the president proposes and what Congress appropriates. And some of that technology R&D is done at the national labs that I'll describe, and some is done with industry. But we'll start with the national labs. That's a good chunk of the money. So they had up to 10 different national labs, and they could invest their money in technology at those 10 different national labs. But the labs all competed against each other and do compete against each other. And they have their own profit and loss statements. So the government decided that it would give certain amounts of money to the different labs, and then the challenge was to be able to integrate all those pieces together and to get the labs to talk to each other and to integrate better and to share knowledge better amongst the different labs and with the Department of Energy. So that's something that I worked on and helped to enable, and we made significant progress. So I want to talk to you about that. And then I want to show you a lot of technical results to show you what the labs are working on and what industry is working on within the shale arena. This talk, some of the slides were put together, a year and a half to 2 years ago, and there have been some advances since then, but let me tell you what was done. So the Department of Energy oil and gas problem works in a number of different areas, as shown on the left. They work on unconventional oil and gas. They work offshore. They work on methane hydrates that could be a huge energy source in the next 15 or 20 years. They work midstream on natural gas infrastructure. And they work on transporting crude by rail and trying to do that safely. As Stella said, you'll have a copy of all of these slides, but we want to talk about the first area here just to show you a fairly well worked out example and to go through some of the technical issues. So we'll talk about developing technologies that can be used to maximize the recovery efficiency and reduce the environmental impact from shale oil and shale gas reservoirs. There are some ancillary issues such as produced water management and so on. So we'll talk about that. Here are some of the key theme areas that the government and many of you may be focusing on if you work unconventionals. As discussed, reservoir management and production enhancement. You may or may not know, but on average, we are only recovering from shale oil reservoirs about 5% of the oil, and we're leaving the rest behind. And in shale gas reservoirs, we're recovering maybe only 10%. So we'll talk a little bit about that today and why that is and what we could do. People are moving more and more towards autonomous sensing, sensing in real time or near real time. There are many ways to do that. One is with fiber at the earth surface, fiber in boreholes, fiber in pipelines. Large amounts of data are streaming into the fiber. How can you analyze and transmit that data properly? And what do you do with it? And how can you make decisions right now with the human in the loop, but eventually autonomously, so that if a fiber senses that a well is going to take a kick, the system recognizes that, and some control system is used to prevent that well from taking a kick and going out. The industry injects various fluids into the earth, including some of the produced water and flowback water, CO2, and so on. In some cases, seismicity is induced. How can we characterize that and mitigate that? In the interest of time, we won't talk about that use case very much today. Some of the technologies that are individually important and that need to be integrated are shown here. Novel geochemistry measurements, full physics and full chemistry multi-scale modeling, combining reservoir scale, core scale, and pore scale, database and physics-based machine learning, and then advanced sensors and real-time data management. The oil and gas R&D office interacts with many different entities: the oil industry, the national labs, the clean coal office. That's actually the office where the carbon storage and the induced seismicity is being funded for historical reasons. They interact with academia, with professional organizations like the SPE, the AEPG, the SEG, ARMA, and other societies, consortia, and then very, very basic, very early stage research on new machine learning methods, for example, high performance computers, quantum computing, that come out from basic research and the science office and from other entities. So how do we get all these entities to work together? Some of these entities work together at what are known as field labs, which we'll discuss shortly. This is the national laboratory system, and if you add up all the dots on this, there are 17 different national labs. 10 of these focus on oil and gas and carbon storage R&D. If you can read some of these words at the bottom, the Los Alamos National Lab works on thermodynamics at nanopore scale and at fracture generation. The Berkeley Lab works on a number of components of this problem. NETL, the National Energy Technology Lab, has 4 different locations around the country. They work on geochemistry. SLAC works on some very interesting chemistry that I'll discuss. And Sandia National Lab works on equations of state. And they work on much more than this. So how do we get all these pieces properly combined? A lot of the basic work is done on the computer at the national labs, at academia, and at private companies like Petrolern and so on that get government funding, and at service companies like Schlumberger and Halliburton, and at oil companies around the world. Then you want to take what is learned on the benchtop and on the computer and really test this out in the field. And this is companies use what are known as technical readiness levels. So this is not level 1, level 2, or it's not a high number, which is ready to be commercialized. It's somewhere in the middle, where individual oil companies or service companies or national labs wouldn't want to invest solely their own dollars to go out and to do a field laboratory. Instead, this is cost shared, and the US Department of Energy pays at least 20% and up to 80% of the cost share these labs. So You see that there's two labs in the overall Permian Basin. There's one with a yellow sort of star, which is labeled Hydraulic Fracture Test Site. That's the orange star that says Hydraulic Fracture Test Site 2, Delaware Basin. And the leader of that, which has gathered a bunch of companies together and gotten some government funding, is the Gas Technology Institute. And then the one shown in yellow is in the Permian Basin, really the Midland Basin, it should be labeled. And so we'll tell you a little bit about what we're doing in the Permian Basin, just to show you an example. There's also a lab in the Eagle Ford. There are some in emerging plays. There are some in predominantly gas plays in the Marcellus. And there's one up in Alaska, which is conventional reservoirs, but unconventional fluids. It's polymer floods and so on. Tuscaloosa Marine Shale Lab is very interesting. It's being led by the University of Louisiana. And they are studying shales with a fair amount of clay and other ductile minerals. These are shales that we're not really producing from these days. But if we could understand the behavior of the more ductile shales, there are many more shale reservoirs that we could bring online with significant volumes of hydrocarbons. But let me go back and show you a little bit about what's going on at the hydraulic fracture test site number 1 in the Midland Basin. At this particular site, these are all the entities that are working together. So you can see the Gas Technology Institute, some of the national labs, oil companies such as Pioneer Natural Resources, the Bureau of Economic Geology, it's the State Geological Survey of Texas, the University of Texas, large oil companies like Chevron, Core Labs, Total, and others. So this was the objective, and there are many slides in other presentations that could cover this. The people who work on these projects, by the way, get a forbearance period for the money that they contribute, then for about maybe up to a couple of years, they get access to these results and can discuss them and use them in their own companies. And then eventually these get shared with industry so that everybody learns. This shows you the objective to really understand the hydraulic fracturing process within the Wolfcamp Formation and to be able to improve the design and execution. How many frac stages do we really need in a horizontal well? Do you know that in some of these shale plays, only 25% of the frac stages are contributing to 75% of the production? And in plays like this, a frac stage could cost close to $100 million. Close to $100,000. And in the Vaca Muerta shale play in South America and Argentina, more than that. So if you could use studies like this to understand where to put the frac stages and how many ones really contribute to production, a study like that in a single well could pay for itself, and then many times over. This is a 4-year project. It's a few years into the project and $18 million spend. So this involves air and water samplings during and after hydraulic fracturing, cross-well seismic surveys, trying different fracture stages, trying to monitor where the proppant is going by using radioactive and chemical tracers, but also coloring the proppant. Also, do you know that more people have touched moon rocks than have touched whole core from the shale plays? It's critically important to take shale core, and there's several hundred feet of core that was examined. And when you look at that core, you understand that the fracturing is really very complicated and a little bit more complicated than how it's been handled in some of the most advanced fracture modeling programs that we have today. There's also pressure sensors that have been used to monitor pressure during production. So now let's talk again about technology enablers, pardon me, and what has been helpful to the national labs. When I got there, I was told that I'd have $50 million to spend on upstream oil and gas, and I asked who should I spend this on? And they said, well, let's start with the national labs. And I said, well, what did my predecessor do? And I won't repeat what he did, but he basically, there were a few labs that he spent most of the money at, and I decided that that wasn't going to work. So I formed a leadership team with decision makers from the top national labs across the country, and basically told them that I would really need them to all work together. One of the enablers that we developed was a knowledge management system where experts and even people that were learning across the labs could share information with each other. And it would be critically important to be able to share the learnings from our investments at the different labs so that we could integrate all the pieces together. We also formed a cross-national lab big data and machine learning team, and then ran seminars with industry to add people to those teams so that it wasn't just the national labs. We've talked about the field labs. Both the coal and the oil and gas programs were studying not just coal and oil and gas, but they were all studying oil and gas reservoirs, as we'll discuss, and it was important to be able to share the learnings across those programs. We held one-day outreach meetings with the upstream industry and then with the midstream industry separately, and built relationships. A lot of the money that we spend goes to these field labs and benchtop laboratory. We built a reservoir modeling program that we'll talk about, machine learning, advanced sensors, and we'll talk again more about the knowledge management. So these are these labs encircled around the Department of Energy, and we built a knowledge management tool. So we built the information technology, and we also built communities of practice. In order to get started, there was already a data system that had been developed. I wouldn't call it really a knowledge management system, but it was developed in order to manage data and decisions from the Macondo oil spill incident several years before this. And it's called the Energy Data Exchange, and we'll give you some references to that. There are various levels of security and protection, and there are some oil companies that interact with the Department of Energy behind firewalls where they're able to share information that they don't want other entities to share. But in this case, we wanted all those national labs to be working together and to be sharing information. Also, as many oil and service companies have, there are lots of people who are retirement age and a whole bunch of people who are new to the system. And how do you share information so that novices and journeyman workers can learn from very experienced people before they leave the company? So we needed to have a data, information, and knowledge repository. When we wanted to build the technical communities of practice, we didn't want to start from scratch. So we actually enlisted the services of Schlumberger, which has a very successful effort since about 1986 or 87 and have won many awards in knowledge management. So we brought Susan Rosenbaum in, and she was until very recently the global director of knowledge management for Schlumberger, and she told us how they had gotten started. So, and she was a resource that we could use as we made progress. We talked to her in October of 2017, and by August of 2018, we already had a system fully operational with over 200 applicants and different topic areas. So if you're interested in machine learning, you can go to that, modeling, you can go to that, field measurements, or laboratory measurements. Very successful. We also looked at both the carbon storage and oil and gas programs to see what we had in common. The carbon storage was looking at trying to contain hydrocarbons and CO2 within reservoirs, and oil and gas was trying to look at recovery efficiencies, but they both have something to do with the flow or lack of flow through the reservoirs. Geochemistry and geomechanics played an important role in both programs. Geochemical tracers were important. Seismic monitoring using new and different waves, long period, long duration was important. So that all got folded in. Now I want to talk about some of the technical work and results. I'm not an expert in these areas, but I'm showing you at the bottom the labs that did this work, and we can give you names of scientists that you can discuss this with. There are many chemical reactions that are occurring at various scales within the rock, at either the fracture surfaces or within the actual shale matrix at pore scale. So you can see a bar on some of these scales. And these chemical reactions result in precipitation of compounds. They are iron compounds or barium compounds, for example. And this causes the formation of precipitation, which reduces the production, both in the short term at the fracture surfaces, the induced fractures, the hydraulically induced fractures, and the natural fractures, and longer term at the pore scale. This can be within the clay matrix itself, or even within the kerogen in the clay matrix. And lab measurements were made that need to be taken out to the field, and there's been some modeling that's going on at various scales. We believe that by understanding this problem of scale precipitation and mitigating or preventing the problem from happening in the first place, that we may be able to significantly increase the recovery efficiency in the shales. And this needs to be checked out at the field labs, which is work in progress. Let me talk about the barite scale buildup. Most of the barite that you see within the formation is actually coming from the drilling mud, as opposed to minerals that are present within the shales. And a fair amount of the drilling mud is left in the formation after the drilling and completion process. And chemicals are used as part of the completion and fracking process, and these tend to be hydrogen chloride. And the hydrogen chloride reacts with the barite and causes dissociation into barium and sulfate ions, and then these ions travel farther into the formation and even into the shale matrix, and they reprecipitate. So rather than trying to attack the precipitation, the labs shown on the bottom are trying to prevent the barium from being released from the mud in the first place. And if you're going to do this, you're not going to change the mud system. Everybody's using barite. But they found in preliminary studies that if you replace the hydrogen chloride with hydrogen sulfate, and then you add a buffering agent, citrate, that you can significantly reduce the amount of barium that's being released, and you can improve in laboratory tests, in any event, the permeability. And a patent's been filed to do that, and that's something that's being tested in the field. So those effects happen at pore scale, at core scale, and at reservoir scale. And we want to be able to integrate various processes, chemical, geomechanical, physical, and so on, over all those lengths and over different time scales. And so we've sponsored work in modeling experiments and analysis at national labs and industry, and looking at field operations, and we need to be able to integrate these things together. Different disciplines can contribute at various scales. The physics and the chemistry and the geophysics and the geomechanics is all coupled. We have field observations. We can use geophysics measurements and geomechanics measurements and pressure measurements to understand the anisotropy in the reservoirs and how the geomechanical properties change in different directions. We can look at pore measurements to look at the scale behavior. We can build models. There are state-of-the-art programs for geomechanical modeling and flow simulation at some of our California labs. Lawrence Livermore and Berkeley is shown on the right side, that do simulation. We can then make predictions, and we can compare them against the field observations. Fiber optic sensing and machine learning also come in, but there's too much stuff to show on a particular slide, so we'll start through this and then fold that in. If the field observations and the data do not agree, then you would revise your models until you get agreement and be able to improve your predictive capabilities. So some of the things that are being modeled with regard to the geomechanics and the flow simulation include where the proppant is flowing in the rock. Okay, the proppant is what's keeping open the fractures. We show that on the left. We look at viscosity and fluid pressure. And on the right, along a horizontal well, we have a number of frac stages that are interacting with each other through what is known as stress arching. So we have to be able to integrate all those technologies together. And studies show that there's strong 3D interactions among the hydraulic fractures and how they interact with the lighter colored fracture system here, which is the natural fractures. So we want to understand the fracture propagation and the proppant flow through these fractures, and how we can make use of measurements in order to understand and monitor and improve the flow of the fractures through the fractures and the proppant. So the DOE has put together an intelligent subsurface engineering initiative where they try to generate and transfer cutting-edge technologies to industry to enable increased recovery. And this will involve distributed sensing and real-time data analytics so that you have early warnings of well failure or that reservoirs in the CO2 storage case are leaking, and for improved subsurface control. And what does that do for operators? It enables the national labs to work on industry use cases of importance to the operators, to assemble enough big data sets to apply the cutting edge machine learning approaches to provide industry with early access to machine learning technologies, and to combine the fundamental understanding of the physics and chemistry and geomechanics of the shale reservoirs with machine learning and distributed sensing. Many people talk about this, and it's really, really important. Until recently, oil companies and service companies were not doing much with big data, and now big data scientists are all over the place, and that's great. But if we want to extract information from the data, we need strong overlap between the subject matter experts and the data scientists. It's not one or the other, it's both. Okay, the data scientists can tell us various tools and approaches to learn. The subject matter experts can tell us what projects and priorities are most important to work on. And then we need to integrate fundamental shale studies with physics-based models and machine learning. Industry has most of the domain experience here. The labs have both subject matter experts and data scientists, and the labs can engage academia and other research organizations. So we need good integration between the SMEs and the data scientists, and we need good integration between academia and national labs, specialty technology companies like Petrolern, service companies, and oil and gas companies. So what does the machine learning do? Okay, small joke, probably a bad joke. When people learned to play the accordion a long time ago, there's a song that they learned to play called Lady of Spain. It goes something like da, 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 da. So there is a cartoon in a famous magazine where a fellow has an accordion and he has a little sign and says, if you give me $1, I will not play Lady of Spain, because it's very annoying. If you go to many seminars on machine learning, many of them are using what's known as the random forest method. I will pay you money to use something more than just random forest. And do you know that the national labs, over all those 10 plus national labs, have more than 1,000 data scientists who do more than just random forest? So you can hire your own data scientists, but you can also learn from and partner with the national labs. So they do shale studies, they do geochemistry, they can handle large data sets, they can keep data secure, and so on. And we've gone through some of that before. Some of the data analytics procedures and approaches are doing more than just database. If you look at this data analytics blob in the middle, it says statistical approaches and machine learning. There's also what's known as reduced order modeling that I want to talk to you about. And when you look at the left, they're looking at field data and lab data, but there's a lot of simulations. If you want to do full physics, full chemistry models, at some point, you probably need access to a supercomputer to generate some models. But you don't have time and dollars to generate huge amounts of full physics simulation models on supercomputers. So you want to use something simpler. You want to generate a small number of models. You want to calibrate them with your data. And then you want to use some approach like neural nets that summarizes all of that without having to spend large amounts of money and time to run full physics models. If I'm sitting with a piece of fiber in a borehole and I see an anomaly, I can't wait 4 days to run a full physics set of models to explain that. I have to use something simpler like reduced order modeling or other proprietary ways of doing physics-based machine learning. And when I combine those models with distributed sensing like fiber optics, I can improve my hydrofracking design, my well placement, my operations, my recovery efficiency. I can reduce costs. And real-time automation can be used to significantly increase recovery, reduce costs, and reduce failures. When we're doing fundamental studies, the studies are being done on the computer. They're fundamental studies. They're at the field lab, and they're data-driven approaches. So we have to be able to integrate those all together, and we have to look at different scales. In the picture on top, we are looking at pyrite, which goes through an oxidation reaction from iron 2 to iron 3 to form iron hydroxide. And that is also filling up some of the pores, so we have to be able to prevent that from happening or mitigate it. That has consequences to changing the geomechanical properties of the rock. When we look at field laboratories, we have academia, we have industry, we have models and we need to validate them. We have cores and cuttings that we need to look at, physics-based models, machine learning, and so on. We need to be able to combine all of those together. If you think I'm not a chemistry expert, I'm really not a microbiology expert, but there's some interesting microbiology measurements that have been done at the national labs, and there are specialty companies that are now working in this space as well. This has been looked at for both the Marcellus and the Bakken. There are different microbial families for the oil and for the gas reservoirs. And the different microbial families may be able to impact the well operations, the reservoir operations, the geochemistry, and maybe even the geomechanics differently. So this is something that's just being looked at and may be part of the whole puzzle. Here's an example. This is a study that was done by some of the national labs and has been at least published in this slide, and maybe it's come out since. This was first done as a data-driven approach and later was done physics-based. The idea was to look at 12 months of production in a bunch of different wells within the Bakken Formation and to look at parameters that could be used to predict, to describe, and then to predict 12 months of production. We wanted to be able to understand the best practices, the parameter values, and so on that would give the best production, so that as new wells were drilled in this basin, that we could get higher 12-month production instead of lower. In the middle were various data-driven algorithms that were used, Bayesian-rich, neural network, linear regression, and so on. On the left are some of the variables that had the greatest influence on the production, including the location of the perf, the length of the perf, the chemical additive, gamma ray, which says something about the shale content, mineral content of the rock. In addition, though, there were variables that were missing. We actually used a commercial database. I will not mention the name, and we took variables from the database and used them. But there were variables that were missing that we found out from some of the previous slides that I showed you were quite important. These are shown in red: total organic carbon, the natural fracture density, and the anisotropy of that network. Are all those natural fractures aligned, or are they scattered, sort of spaghetti shaped in the well? In the reservoir, the injection rate was important, the type of fracking, pyrite that was present in the rock because of the iron 3 hydroxide precipitation and scale buildup, and the microbe family. We'll get you further slides from this work, but those were used in order to characterize the production and to improve well placement and production from the reservoirs. When companies work together, or when they work with the United States government, there are always issues of data security and data anonymity. So it's important to maintain the confidentiality of the data that comes from the partners. It's important to be able to secure the data and to provide computational resources for the partners. And so some studies that are published in the literature will probably be done in part with synthetics that have been calibrated to real data sets, and in part by making the data anonymatized, okay, removing certain labels so you can't track back where it's coming from. One of the last slides that I have here on integration has to do with sensors, fiber optic and other sensors. There are 4 laboratories that are working on this. And if you want to learn more about fiber optics and sensing and the types of measurements that we make with them, temperature, strain, acoustic, chemical, electrical, and where this whole real-time measurement effort is going, I'm giving another talk, I think it's 21st, and it will be on advanced sensing. And this is one of the slides from this talk. But we had to get these labs to work together and to integrate. NETL is working, among other things, on chemical sensing, which is important to see, for example, whether pipelines are starting to be corroded and whether eventually the pipes will crack and hydrocarbons will be emitted into the atmosphere. On the top right are measurements that have been made by Berkeley Lab, both to monitor CO2 storage and new systems and studies to monitor fluids in shale reservoirs. And at the bottom on the left are studies that are being done using what's known as quantum sensing that we'll talk about next week, where you have improved signal to noise and may be able to monitor weak signals in CO2 reservoirs or in oil and gas reservoirs using quantum sensing. That may be coming up fairly soon. And then Lawrence Livermore Lab has a facility to design, model, fabricate, and process fiber. It's what's known as a draw tower. And then they're using data analytics, which is a good example of integration. And let me show you this as probably one of the last few examples. We talked about the fact that it would be useful to run a bunch of full physics chemistry models multi-scale on a supercomputer somewhere, but we just don't have the luxury and time in the application stage to be able to do that and apply it in the field. So you generate a small number of representative models, and there are various schemes, proprietary and otherwise, to do that. You combine that with actual data so that everything is calibrated, and then you use some sort of a procedure. It could be regression analysis, a neural net, a lookup table, whatever. You train on a small number of simulations, and you are then able to take inputs to a simulator, run it through a description like a convolutional neural net, and to be able to come up with predictions that can be made in minutes or seconds as opposed to hours or days. This is the final example. Imagine that I want to put fiber in a borehole and use it to make measurements. And on the right, I want to be able to understand the height of major fractures, their length, and where the proppant is going. So on the left, we run our geomechanical modeling and flow simulation programs, and we look at the waves that are generated, low frequency and microseismic, that would be recorded into the fiber. And because we don't have a lot of measurements to begin with, we also supplement this with a synthetic catalog. So these are responses for different fiber locations and different types of waves in the borehole. And we show in the second part of this an input signal and various attributes that we can measure. We then take the attributes and put them through a deep neural net, and then use those to make predictions and validate them with real data sets. This tells you where to put the fiber, and it tells you how to interpret the fiber. So the goal is to develop automated real-time characterization of fracture development, and to be able to respond to that and to optimize production. Machine learning requires large training sets, and some of the shale data sets are just not large enough, so we supplement them with models. So that lab is generating a catalog of measurements to serve as a training set and applying them as I described. As a summary, technology integration and collaboration are critically important to the success of many projects. There are technical, organizational, and psychological barriers to overcome. You may have heard about the problem of herding cats. It's important to herd all those cats so that they all work together, not just fight with each other. Integrated cost-shared field laboratories have been successful in enabling oil companies, service companies, and labs to all work together and to share the cost at fairly early stages of technology development. And knowledge sharing and building platforms and communities of practice are important. I've listed here and have gone over some of the technologies that were important, and it was important to integrate these together into a whole system approach. And hopefully over time, we will learn more and more about how to characterize the shale reservoirs and how to improve health, safety, and environment, and to improve the production and recovery from these reservoirs. I thank you very much for your interest, and I'll be glad to take some questions, answer the ones that I can, and get you answers to the ones that I'm not able to. Thank you very much.
Thank you so much, Dr. Cohen. That was a very informative presentation. Thank you for taking the time to make that. So we have still a few minutes left, and we can take a few questions. Any questions from participants? Please, if you have a question, write it down to the public chat so I can read it for Dr. Cohen. I have one question from Hamid, and the question is how companies can get involved in these government-funded projects.
Yes, so the government wants to be fair to all companies. So when I was the director, even though I had worked at Shell, I can't call up Shell and say, you know, you really ought to work with Stanford on chemical problems together. And what we do is we encourage the national labs to go out to conferences like ERTEC, like AEPG, for example, SPE, and give papers. That usually causes the oil companies to come and talk to them. And that's the opportunity at that point for the government and for those labs to say, why don't we work together? There is something called a funding opportunity announcement process, FOA, that comes out from the federal government. And industry oil companies, specialty companies, academia that's interested in knowing when the next FOA is coming out. It could be CO2, it could be other aspects of shale reservoirs. If you get on the reference list by sending a letter to an email to the Department of Energy, they will get you on the list. Once you see that that comes out, then I've mentioned to you a number of labs that you might want to contact. You can reach out to those labs, and those labs reach out to industry. So it's really up to your community to make those linkages. And I will tell you that when it comes to a large FOA, as opposed to a smaller small business or technology commercialization funding from the government tends to prefer groups of companies, academia, and national labs that are all working together. So that's kind of how it's done. But the government can't bias it by saying, hey, Petrolern, you ought to talk to this, that, and the other. So that's one of the reasons for giving this presentation, although I'm no longer present at the government. Reach out to the Department of Energy, get on the list, and start to communicate with these national labs who will then link you up with other entities. Sorry for the long answer, but it's an important process, and I wanted to explain it correctly.
No, thank you. So another question that we have is, with current low oil price and economic impact of COVID, what do you think DOE budget will look like in the near future for fossil fuel R&D projects?
The budgetary process starts with the President of the United States, who makes a recommendation, and then it goes over to the to Congress, to the House, and to Senate. I can't predict that, and I don't know what it will look like, but my recommendations, if anyone were to ask me, would be that in a low oil price environment, technology is extremely important. If oil prices are $200 a barrel, some people are just going to throw the technology out. Whatever they're doing is making money, and they don't want to slow themselves down for technology. But when you talk to some oil companies and say oil prices are low, would you like to invest in technology? They say, well, wake me up when the oil price goes up. And actually, proper funding of technology at low oil prices is what is critically needed. Why do I need all those non-productive frac stages, for example? Why do I need wells that are not optimized in terms of their placement so that there are parent-child frac hits between them, which in most cases are detrimental and in a few cases actually help. I can't discuss that part. But this is where technology is really important. And I was in a meeting with the Department of Energy that I can't quote with, and many other companies were in that meeting, and we basically made recommendations of the type that I just made. You know, please, you folks, if you are living in the United States, all have congressmen and senators, and it would be good to tell those people that this technology needs more funding, especially at low oil prices.
Thank you. So we have time for one more question. And the question is, how do you see the scope and importance of data science in petroleum industry?
I'm sorry, you have to repeat that one more time. Say again.
How do you see the scope and importance of data science in petroleum industry?
Data science.
Yes.
Yeah. Several years ago, before there was an Oxy and an Anadarko that merged, the head of Anadarko at the time said, I'm going to start hiring data scientists. And they said, why? He said, because on a good day, we're not using more than 5% of the data that we acquired and processed, starting with the seismic data. It's just sitting there. We need to be able to extract information from the data. Another aspect is humans have their own way of interpreting data, and an interpretation is just that. It's not an absolute 100% correct answer. It's an interpretation. And the thought patterns of humans for geology and sciences like that need to be part of the process. But there needs to be an objective way of working through the data. Data science may tell us new spaces, reduced dimensional spaces, in which we could look at data that humans hadn't thought of. Okay, by mapping all the fundamental equations into reduced dimensional spaces, there may be ways of finding small numbers of attributes. An example of that is reduced order modeling that will enable you to extract information from the data that you might not have thought of. You just be sitting there running all these full simulations on a high performance computer until somebody told you that you had no budget left or it was there wasn't much time. But this is the talk on integration, and my last thought is the data scientists are vitally important, but so are the subject matter experts, and we need to bridge between them so that they learn from each other, and the best of both are used to help make the best decisions for oil and gas and for carbon storage. So with that, I want to thank you very much for your attention. We will make copies of these slides available. The ones that have the national labs on them are all in the public domain. I got them from the public domain and I put them in this talk. And we'll give you names of people you can follow up with in government because they'd be glad to talk with you about this. Thank you so much.
Thank you, Alan, and thank you everyone for joining us today. Please make sure to follow us on LinkedIn to receive updated information about the upcoming P.A.S.S talks and other news, other good news from us. With that, I wish you all a good Wednesday and hope to see you all on Friday.